The topic for today is trig ratios with circles. First, a little reminder, our tangent ratio is defined as the opposite side length over the adjacent side length. You can also think of this as steepness of the triangle. So both these triangles are have 31 degree angles. You think you can see they have the same steepness. One is bigger than the other, but they're equally steep. For this one, the tan ratio is the opposite, which is 6, over the adjacent, which is 10. Whereas with the smaller triangle, the tan ratio is the opposite, which is 3, over the adjacent, which is 5. So exactly the same ratio, 6/10 or 3/5 means the same thing. In general, if you have the angle, then you can use the tan function on the calculator to get an excellent estimate for the tan ratio. On the other hand, if you have the tan ratio already, you can use the inverse tan key on the calculator to get an excellent decimal estimate for the angle. Another reminder, a tan ratio can also be defined in terms of a circle. So if we have a triangle, it's the opposite side of 55.3 divided by the adjacent side of 8.5. We look at a point on the circle that goes with a 32-degree angle. Remember, we always start here for our turn. So turning 32 degrees, this is the coordinates for that point. The adjacent side here would obviously be that x-coordinate of 8.5. And this length of this side here would be the same thing as the y-coordinate for that point of 5.3. So either way, with this 32-degree angle, we're going to get a tan ratio of 5.3 over 8.5 and 5.3 over 8.5. Also, if you look at it carefully, this triangle right here is actually kind of hidden inside the circle here. So we're really doing the same thing whether we use a circle or a triangle in this case. Continuing with trig ratios with circles, the key techniques we're going to look at here are dropping an altitude to make a right triangle, using Pythagorean theorem, SOHCAHTOA, and symmetry. You might want to pause the video and read through these more carefully. When you look at this fully worked out example, they asked for the cos ratio, so we needed the x-coordinate divided by the radius. The radius is easy in a way. I can just count the tick marks to see that this point here would be 5, 0. So if this is 5, so is this. They're both the radius. To get the x-coordinate for this point, I'm going to use this triangle, right? So I dropped an altitude, and I used a little bit of Pythagorean theorem to get that missing side of 1.71. Of course, it's going to be negative. 1.71 is a coordinate. Moving on to the angle here. I'm going to highlight the red question mark here. I'm going to get that angle first. One of our key techniques is SOHCAHTOA. So there's a right triangle. The sine ratio for that question mark angle is 4.7 over 5. A little inverse sine gets me 70 degrees for that little angle. The one I really want, though, is theta. So this guy is going to be 180 degrees, right? If we kept turning here, we'd have 180. But I need to subtract out that little 70 part. So 110 is the value for theta. For the turn that goes with point B, notice point B is symmetric with point A. They have exactly the same x-coordinate, and their y-coordinates are opposites of each other. So this y-coordinate is positive 4.7, this y-coordinate is negative 4.7. So writing down the sine ratio is very easy for that. It's going to be negative 4.7 for the y-coordinate here, and 5 for the radius, just as before. Oops, sorry about that. For the amount of turn that went along with point B, I'm going to move over here to a separate little picture. The thing to notice is that this little turn here is the same as this little turn there due to symmetry. We know the little turn up there is 20 degrees because we knew that angle A went, or point A went with a 110 degree turn. So this is 90 to here. So this must have been another extra little 20 there. So for point B is going to be 90, 180, 270. Oops, that went a little too far, right? So not 270, 270 minus 20, which is 250. And that does it